Yeah, so what we are going to start today is recursion. And let me tell you, once recursion starts, it will never end, okay? Because without recursion, you cannot understand sorting, you cannot understand linked lists, you cannot understand trees, you cannot understand heaps, dynamic programming, some greedy algorithms and graphs. So without recursion, you cannot understand anything. That is guaranteed. So this is very important topic, and try to understand this very well. So this is going to be very important for you. Now, what exactly is recursion, that we'll try to understand. First, I will talk about very simple things, okay, because all the questions that I will show you, they will be nothing but an extension of those small things. If you understand them in deep, then you can solve the questions very easily, okay. So what happens is that whenever, let's say, there is a function call, as simple as, let's say, there is a main function and there is some other function func, and this main function invokes this func. So what happens, immediately the control from here passes on to here. This is what happens, right? So there are two things which are in picture. What are those two things? First thing is caller function, which in my case is main, and then the second thing is called function, which in my case is this func, okay. So caller can pass certain arguments to the called function, okay. Let's say it passes x, and this called can return something back to it. Now the reason I am adding this word can is that it is not necessary. Sometimes this func can be a void function also. Void function means it doesn't return anything, it simply does something and then it gets over, okay. And passing arguments is also not essential, because there are some functions which don't accept any argument. You simply call them and then they do their job, okay. So there are two things in picture. Now whatever the caller passes, that is passed to the called function, and whatever the called function returns, that is returned to the caller. I can also refer to this as parent and child. This is my parent function and this is my child function, okay. Remember this word very clearly. Whatever the child returns, that is returned directly to the parent, not to the caller of this. So it might have happened that there was some other caller dash, okay. So whatever it returns, that doesn't go to this unless or until this specifically returns it to this, okay. So this thing you have to keep in your mind, okay. Now I'll maybe start with a very easy example, which was about computing factorial of a number, okay. So I'm just going to write down the code of that. Let's say there is a function factorial that takes in a number n and returns me the n factorial, okay. So how is the n factorial being defined? N factorial is equals to n multiplied by factorial of n minus 1, right? This was the rule. This particular thing, this is also called as what? Recurrence relation, okay. Recurrence relation means your ability to relate the solution for a large problem to the solution from a small problem, that if this is known, I can derive this also, okay. So now this particular thing is not applicable for all the values of n, right? F of 0 can't be written as 0 into f of minus 1. So wherever the recurrence relation is not applicable, that is called as base condition or termination condition. And the best practice of writing recursive code is always you should write the base condition or termination condition first, okay. So what will be my termination condition in this case? If at any point of time my n is 0, I should be returning fact of 0. And what is factorial of 0? That is 1. Otherwise, I am free to return n multiplied by fact of n minus 1, okay. So this is the way the code for factorial is written. Now if you take a look at this, so what is essentially happening is, let's say the call from here was for fact of 5. So there is a main function to start with. This main function invokes fact of 5. Now once this fact of 5 has been invoked, where will it go? Will it go to if or will it go to else? Will it go to the other part? It will go to the other part, right? So since it goes to the other part, in that it will make invocation for fact of 4. Okay, and now see, main is waiting for this to complete, this is waiting for this to complete, so both of them are waiting for this to complete. Similarly, when fact of 4 would be called, this fact of 4 would again call fact of 3. Now all of them are waiting for fact of 3 to complete. Now fact of 3 will call fact of 2, this will call fact of 1, and eventually this will call fact of 0. So see, in any recursive code, the call flow happens from top to bottom. I call this as top and I call this as bottom. So the call flow is from top to bottom. But now when the returning happens, can you tell me which will be the first function out of these which will return a value? It will be f of 0, right? And what will happen for f of 0? This condition will become true and this condition will make this return 1. This one will get returned to its parent. This one has still not made its way up till here or here or here or here or here. This is just right now captured by this function. Now it is up to this function that what it wants to do. Okay, it can return it to its parent or it can change it to something and then return to its parent. It is totally up to it. Okay, so one thing that I can say is that termination condition is the reason because of which the return flow starts. If you don't write the termination condition, then the return flow will not start. Okay, so it is very, very important. And the return flow happens from bottom to top. So see, the call flow happens from top to bottom and return flow happens from bottom to top. So now when f of 0 has returned this value 1 to f of 1, what will f of 1 do with it? So if you look at what would have been the case for fact of 1, it would have said that, hey, I'll return 1 into fact of 0. Now fact of 0 has been returned, that is 1. So it would now want to return what? It would now want to return 1 into fact of 0. So that is 1 into 1. And to what will it return that value? It will return that value to its parent, okay, which is this. So 1 into 1 will get returned to this fact of 2. Now what will fact of 2 do? So fact of 2 would have said that, hey, I'll return 2 into fact of 1. Okay, now fact of 1 is this value. So it will multiply this thing with 2 and return it to its parent. And now see, whatever these functions are returning, that is the factorial of that value. So factorial of 0 is 1, that is the reason it returned it. Factorial of 1 is also 1, that is the reason it returned it. Factorial of 2 is 2, that is the reason it returned it. Now similarly, what will factorial of 3 do? It will multiply this thing with 3 and return it to its parent. Now similarly, what will this do? This will, whatever answer it gets from its child, that answer will be multiplied by 4 and it will return it to its parent. And similarly, this will multiply and it will return to its parent. While talking about time and space complexity in a class, I talked about one thing, that whenever you write recursive code, how does your operating system ensure that these function calls are somewhere there in the memory waiting for each other to finish? It uses a stack, yeah. So corresponding to every function call, there is a stack. So this main would be there at the bottom of the stack, and then f of 5, and then f of 4, so on till the top, f of 0. And now you will realize it in a more concrete manner, because the first thing to return is the last thing. That is the reason it is in the form of a stack, so that f of 0 gets removed first, then f of 1, then f of 2, and so on. That is the reason stack is used to implement this recursive call. Okay. Now, if you understood this thing clearly, the space complexity will be order n, because here I saw that the maximum number of functions that were in the line waiting for each other, that was almost order n. Okay, that is the reason the stack size can be of order n. Now, what will be the time complexity? Okay, so you can say order n. The easiest way to say that is that how many levels are there? Can I say that, hey, approximately order n levels are there? And in every level, just one multiplication is happening, isn't it? But can you think more exactly and then try to tell that will the time complexity exactly be n, or will it be slightly higher than n? It will be slightly higher than n, order to n. Why? Because first these function calls will get inserted into the stack. So first main goes, then this goes, then this goes, and then this goes, right? So first you insert n values in the stack. How much time does it take? If you have to insert n values in the stack, how much time does that take? Order n. And then you remove those values from the stack, isn't it? The function returns, that is exactly what you do. Whenever a function returns, that is popped out from the stack. So if you pop out n function calls from the stack, how much time will it take? Order n time again, right? So order n time for push, order n time for pop, and then there will be order n time more for performing these multiplications. So it will be somewhere around 3 into n push, n pop, and n arithmetic operations. Yeah, what will be the space complexity? We can clearly see that we have used a stack, and how much has that stack grown? It has not grown more than n, okay? And every time what is happening, that what does this stack contain? This stack contains the function calls, and those function calls are stored by, you don't need to know that much, but you can study if you want, the pointers to the function calls. So there are pointers to functions also, okay? And that is like order 1 space. So if there are like almost order n pointers to functions, so that would be around order n space complexity that you would require.